Hello and welcome to the first episode of USask Science. The University of Saskatchewan is a predominantly agriculture-based campus with a heavy emphasis on novel agronomy and the breeding of uncommon commercial crops. This is a 4-part series that will be dedicated to the research reports made by this university. Let's get started. In Western Canada, there was a gradual increase in the use of intercropping, the process of growing two crops in the same field. In this case, the method involves growing a legume crop such as peas or beans with a non-legume like wheat or canola. The main ambition was to reduce the presence of disease within a field. Several researchers in the 80s found that the amount of nitrogen uptake in the non-legume crops increased, as well as an overall increase in yield. It was also found that non-legumes help prevent lodging in the legume crops by providing a location for the legume to climb on. By the way, lodging is when a plant falls over. So if you see a crop you're growing fall over, you know what to call it, lodging. But I digress. The ambition of this paper was to determine the effects of intercropping of legumes with non-legumes. The study utilized 5 fields and 5 intercropping systems, which can be seen on screen right now. These were compared against monocrop fields. The results confirmed one of the chief assumptions within the project. The reduction of legume lodging was noted on each site. Pea tendrils successfully attached to canola, mustard, and oats. Lentils did not, however, extensively climb flax, but the flax did hold the lentils upright by giving physical support to the lentils. One of the findings did show that intercropping only works if a strong stem cultivar of a non-legume is used. In the research field known as Meadow Lake, the cultivar tribute was used. This cultivar has a weak stem, and when the peas climbed onto it, both the canola and the peas lodged. Overall, intercropping seems to stabilize yield by providing a buffer against the perennial problems that cause yield loss in Western Canada. These seem to be primarily disease and lodging. From the perspective of fertilizer use efficiency, the monocrop non-legume crops were the most efficient in fertilizer use. Legumes were the least, and intercrops are somewhere in between. However, the intercropping process seems to have triggered an increase in nitrogen fixation in the legume crops. Overall, the yield of the crops are lower in the intercrop system than the monocrop system across the board. But the yield was also stabilized, creating a buffer that limits yield loss. This indicates that this method may increase or stabilize yields in poor agricultural locations. That about covers everything. Thank you for watching. Hello and welcome to another episode of USask Science. In the 90s, there was a great need for a new crop to be added to the spring wheat system of agriculture in Western Canada. Due to the semi-arid climate of Western Canada, the crops must be adapted to a water-limited environment. Otherwise, they would not be an ideal candidate for an alternative crop. During the 90s, the primary cropping system was mostly consisting of spring wheat. The pea has been reported to yield well in water-limited conditions around the world. In the prairies, research results from the organization called Swift Current and Scott, and various testimonials from producers seem to echo the potential use of peas as a crop in Saskatchewan. Within this historical paper, drought tolerance was defined as the ability of the crop to make yield efficiently from a limited water supply. This is represented by 16 genetic traits associated with drought tolerance, seen on screen right now. The amount of drought tolerance in total is defined by an equation seen on the next slide. Water use efficiency is defined as the amount of above-ground dry matter produced per unit of water, and the harvest index is a ratio of yield to above ground dry matter. Dry matter being the amount of plant material left over after the water is removed. Water transpired is the amount of water that leaves the plant through respiration and other factors. Water transpired can be reduced by increasing the size and depth of the root system. Through the alteration of osmotic adjustment within a species, leaves can retain more water and by proxy increase drought tolerance. Species with shallow root systems in the presence of irrigation will reduce drought tolerance. Peas have a longer water retention period in comparison to other crops like wheat. Hello and welcome to another episode of USask Science. In this episode, we'll be covering the history of forage testing and forage breeding in Saskatchewan. The original forage testing began in the 1920s in Saskatchewan. These early experiments were simply put the acquisition of forage cultivars introduced from Northern Europe and Eastern Canada, which were then tested using traditional cropping system experiments. These crops did not persist or yield well due to a combination of drought and cold winter temperatures found in Saskatchewan. As a consequence, forage breeding began in the 1930s at the University of Saskatchewan under Dr. Kirk. The first breeding program released the Cultivar fairway crested wheatgrass. The testing was done in Saskatoon and federal research stations, but uptake after it was released was rapid and extensive. This forage was used to reseed and revitalize old soils that were degraded in the Dust Bowl era during the Great Depression. Crested wheatgrass became a very useful mechanism in order to prevent erosion and provide feed for cattle. World War II, however, interrupted these research programs during the 1940s, but after the war, new graduates with PhD degrees became part of the new large-scale project to breed new forage crops, and the forage research programs were reborn under the Saskatoon and Swift Current research stations. The program quickly expanded, utilizing other forage crops such as smooth brome grass and intermediate wheatgrass. Swift Current would also breed intermediate wheatgrass and Russian wild ryegrass in order to improve the amount of variation in terms of forages. And both research programs would develop new alfalfa cultivars. Swift Current focused on the creeping-rooted alfalfas for drought-prone southwestern Saskatchewan, while the Saskatoon research station focused on taproot alfalfas with higher yields for the Parkland region. Saskatoon also had minor research programs for breeding sweet clover and slender wheatgrass. Testing of these new cultivars was done primarily through the federal government in Saskatchewan during the 1950s. But there was also the addition of federal stations that had demonstration farms located on private farms where additional testing was done, and field days held to extend the results and show off the new varieties. The plant breeders would utilize coordinated cultivar trials that required the test to be replicated on each site so appropriate statistical analysis could be utilized to confirm or deny its viability for use in Saskatchewan as a commercial crop. Due to the technological limitations at that time, calculations were done using mechanical calculators, so statistical analysis was a winter activity and the results were published a year after the data was collected. As a result, the tests were very small in nature, with only a few entries per cultivar or species. These varieties were compared against the cultivar known as vernal alfalfa, and over time, these research organizations would begin to incorporate and test cultivars, specifically of alfalfa, bred in the United States. In the 60s, budget constraints in the breeding programs would reduce the amount of off-station cultivar testing. This would correspond with an increase in the private sector for breeding new varieties of forage, especially alfalfa. Improved technology would also allow for even greater levels of testing, and each location could conduct larger tests with less labor thanks to new plot drills and forage plot harvesters. These were done through the federal research stations known as Indian Head, Swift Current, Scott, Saskatoon, and Melfort. The cultivar that was used for comparison purposes shifted. In the Parkland sites, it was shifted to Beaver. In Swift Current, it was shifted to the cultivar Rambler. Swift Current would also do the first irrigated alfalfa trials in the history of Saskatchewan. The best cultivars would be recommended to the farmers by the plant breeders and testers themselves under the Guide to Farm Practice publication. This consisted of only a few cultivars per species, with the exception of alfalfa. The efficiency of this breeding program was improved in the 1970s even further by the use of punch card data storage. This reduced the analytical labor required to make a statistical analysis of the trial results. At this time, the amount of United States cultivars of alfalfa were increasing in terms of use within Saskatchewan, with the regular breeders taking the back seat. At this time, the private breeders were required to go through the government trials in order to be established as a variety within Saskatchewan. And due to the new technology being expensive, they had to pay for that privilege. Consequence of this reality is that by the 80s, forage testing and breeding was mostly done by the public sector, government organizations in both the United States and Canada. But by this point, private companies could obtain testing for free. But as a result of the increasing costs, Scott, Indian Head, and Melfort research stations dropped out of the program, leaving only the larger groups and research stations to do the testing. The researchers codified their work into a single program called the Saskatchewan Advisory Committee on Forage Crops and its Variety Testing Committee. Later on, private breeding companies, farmers' unions, and the provincial government would be incorporated into the decision-making process within this system. This became known as the Saskatchewan Forage Council. In the 90s, two major changes happened in forage cultivar testing. First, the Saskatchewan Forage Council obtained funding from the federal government, granting the provincial government and their research stations additional testing sites, enough funds for full-time technicians, summer students, and travel costs and lab analysis costs, and the introduction of the new NIRS techniques and technologies, which can be used to analyze the forage quality produced by the cultivar. The testing system was also further refined into the WF test to more readily incorporate this new technology. Eventually, this program was assimilated fully into the AAFC organization, which is the federal organization dedicated to agricultural research. As a result, the forage industry research included 4 Saskatchewan research stations: Melfort, Saskatoon, Swift Current, and Outlook. But there's also 4 sites in Alberta and 3 in Manitoba. There was once more a testing fee for both public and private entries to cover the cost of testing. The new computerized testing system would also shorten the research process and analyzation process so that the trial data could be incorporated into the research publication by the end of the calendar year. During the 90s, the philosophy of extension changed. The forage scientists would no longer recommend cultivars. Instead, the information was published, and the producers could make their own selection of cultivars based on performance data. This became the standard until 2011, and since 2011 there have not been any new cultivar trials in the WF testing system. There have been very few new cultivars submitted, and not enough to justify cultivar trials. This was a product of the consolidation of the seed industry, with fewer companies selling seed of forage cultivars. In addition, another agriculture regulation board, run by the federal government, were making regulations that were moving towards forage cultivar registration that did not require merit testing and this was implemented in 2014. As a result, the testing of newly bred cultivars for commercial production became decentralized and no longer standardized. But as a result, there's very little data on the new cultivars that have been released since then. And in 2015, several unions and organizations within the farm and science community identified the fact that there is too little data to accurately identify which cultivars are a winner and which cultivars are a loser in terms of testing. And as of 2015, they're developing a new standardized method to test the cultivars. But it may be for naught because the interest in new cultivars within the forage industry is dwindling, with most farmers purchasing older varieties like Algonquin and Rambler alfalfa. And there's little, if any, demand for new cultivars of forage. And that will covers everything. Thank you for watching. From a water use efficiency standpoint, crops that alter their physiology to a drought environment are more capable of surviving in such an environment. Plants that can rapidly absorb moisture closer to the surface prior to evaporation will also have such an advantage. Peas have these traits to a greater degree in comparison to wheat. The harvest index values are typically larger for peas in comparison to spring wheat. This has far more to do with the genetically programmed differences in plant growth patterns. This includes the fact that this species is far more conservative in the production of biomass in comparison to wheat. Overall, wheat produces more leaf, shoot, and root material than peas. Wheat yields better when babied in the context of Western Canada, but pea will yield a similar amount of seeds in comparison to wheat under less ideal conditions. And that about covers everything. Thank you for watching. If you want to donate to my channel, the links are below. If you want to buy my book, you can also find that link in the description box below. Hello and welcome to the final episode of USask Science. Lentils have been grown in Saskatchewan since the late 60s. This paper was written by Dr. A. E. Slinkard of the University of Saskatchewan in Saskatoon. This paper dates back to 1979 and details the history and management strategies of lentil in Western Canada. As I'm sure you're well aware, much has changed since 1979. Herbicide names change, herbicides and pesticides in general are either changed in formulation or dropped off the map entirely, and new improvements are made in agronomy, and so on and so forth. As a consequence, the paper I'm referencing may not be wholly accurate to the way lentils are grown in modern times. However, this paper should be considered a time capsule to the history of lentil production within Saskatchewan. And as this is a history and science channel, I think everyone here will appreciate this video. Let's get started. Lentils were first grown commercially in Saskatchewan in 1969. During this era, only 160 hectares were grown. By 1972, it reached over 6,000 hectares. However, the promotion was too soon. The management strategies were not fully developed yet, including which herbicides to use, what fertilizers to use, when to plant, how to plant, and so on and so forth. As a consequence, the late wet springs of 1974 and 75 resulted in low yields, early fall frost damage, and several other problems that nearly eliminated production of lentils within Western Canada. However, a few farmers were able to consistently produce good lentil crops in Saskatchewan, providing hope that, at least in certain areas, Saskatchewan could still grow lentils. In the interim, the University of Saskatchewan was still studying the different herbicides available at that time to find the best one suited for use in lentils, as well as developing a full package of agronomic practices that would be utilized by the farmers. The full details were published in the University of Saskatchewan Extension Division publication 382. This was co-written by the successful farmers in Saskatchewan that are producing lentils between 1969 and 1975, the Pioneer Grain Company, and University of Saskatchewan itself. It was found that lentils are best adapted to different parts of Saskatchewan, especially in comparison to faba beans. Faba beans have a long growing season requirement and cannot tolerate drought or salt, making them well suited to the southern parts of Saskatchewan in irrigated or heavy clay soils. Peas are best adapted to the black soil zone, which includes parkland within Saskatchewan. Lentils, however, have some drought tolerance and do best in the dark brown soil zone found in Saskatoon, more specifically the south of Saskatoon. Lentils have an indeterminate growth habit and will continue flowering and growing until the plant is stressed by drought, nitrogen deficiency, heat, heavy pod set, or competition with weeds and root rot. As a result, droughts are used to terminate vegetative growth and mature the seeds in August. This makes growing lentils quite predictable and controllable. The major cash inputs needed for lentil management are the seeds, the fertilizer, and the herbicides. There's a seeding rate of 56 kilograms per hectare, or 50 pounds per acre, of seed. The next cash input is herbicides. Lentils are slow growing, short, and are very poor competitors with weeds. As a consequence, chemical weed control is required. And since it was found that lentils grow best in stubble, which is the remnants of the previous year's crop, there's an increase in weeds, since no-till increases weed production. As a consequence, several herbicides have been registered for use of lentils, which include Barban to control wild oats, Sinox for post-emergence broadleaf weed control, and the brand name Hograss for post-emergent control of annual grassy weeds outside of wild oats. Hograss also controls wild mustard pretty well as well. If this herbicide is to be used, it should be done prior to the lentils reaching 5 to 7 centimeters in height. Otherwise, it will burn quite extensively. During this time, the researchers were also experimenting with other unregistered herbicides, such as Avendex BW for wild oat control, Driftland for broadleaf weeds, Sencor for broadleaf weeds, and Metribuzin for broadleaf weeds as well. The main management techniques has been written down and will be seen on the last slide of this video, but that about covers everything. Thank you for watching.